So the next talk in this session is a contributor talk by Suvronil Datta, who is from IISc Bangalore.
First, I would like to thank the organizers for giving us this opportunity to present our work on nonlinear transport in graphene heterostructures. I would also like to thank the previous speaker for introducing these MoirÃ systems that we will be discussing. And I would like to thank Professor Avadesh Narayan, who was yesterday's speaker. He basically for elucidating these theoretical concepts of nonlinear Hall effect and Berry curvature dipole, which will help me to explain this topic. Okay, so I will start by introducing the experimental probe that we will be using and why it is important. So this regular classical Hall effect and quantum Hall effect, you all know, we are basically flowing a current in presence of a perpendicular magnetic field, and we are measuring the transverse components. In case of anomalous Hall effect and anomalous quantum Hall effect, we don't put any external magnetic field, but in certain material, the internal magnetization actually creates this kind of transverse responses. Now, all these different Hall effects has in common is the broken time reversal symmetry, which in turn create this Berry curvatures, which basically comes in this equation of motion. This extra term comes, and we get this Hall resistivity in terms of Berry curvature. In case of anomalous Hall effect, not only these intrinsic effects, but the extrinsic asymmetric scattering like skew scattering and side jump mechanism also contributes to this anomalous Hall effect. In fact, this anomalous Hall resistivity can be expressed in terms of this summation of difference contributions. In addition to that, this different terms varies differently with the scattering time, which enables us experimentalists to isolate these different terms. Now, all this thing has in common is the broken time reversal symmetry. We want to realize a similar transverse response in a system where this time reversal symmetry is preserved. Now, under time reversal symmetry, if the inversion symmetry is broken or not, for this first order component is always goes to 0 because of this when you take this full momentum space integration, which make this sigma xy vanish. Now, we will basically look at the higher order terms. So first, is this? Yeah. For the nonlinear Hall effect, first thing that we'll do is to break the inversion symmetry. The initial formulation is very similar. You have this term Fk, which is basically the occupation function, and this velocity term includes the Berry curvature, which I showed earlier. This was shown by Sodman and Fu in 2015, which shows that this 2 omega component, basically the second order response in the current density as this chi ABC, which is basically the conductivity of the second order multiplied by this electric field square. It is the analog of the J equals to sigma E in linear response. If you simplify, this chi ABC can be expressed as an integration of this derivative of the Berry curvature, which actually is known as the Berry curvature dipole. This tells that even if the whole Berry curvature over the full momentum space is 0, the Berry curvature dipole can be non-zero and give this Hall response, but in the second order. Now, similar to anomalous Hall effect, we see the scattering also includes in the picture. So, in a system where this inversion symmetry is broken, you can have these two electrons with different chirality. If they are in presence of a disordered potential and going opposite to them, in that case, there will be scattering. And this scattering is asymmetric, means that the scattering from k to k prime will be different from minus k to minus k prime, which is the skew scattering. This in turn basically give rise to this nonlinear response, not only in the Hall direction, but also in the longitudinal direction as well. So we'll talk about this nonlinear transport. Now, it can happen at different values, which is shown by these red and blue circles. And the side jump scattering mechanism also contributes to the nonlinear transport. Just to summarize, we are basically flowing current in a system where there is no external or internal magnetization. Basically, the time reversal symmetry is preserved. And for the Berry curvature dipole, we are basically getting this Hall response in the 2 omega. And for the extrinsic scattering, which contributes to both the Hall and the longitudinal component of 2 omega in terms of Vxy 2 omega and Vxx 2 omega, we are basically measuring these components using lock-in by setting the harmonic at 2. Okay. Now, these are the initial candidate materials which were predicted to have this phenomena. We will mainly look at these graphene-based heterostructures. The first study showed this effect in WTE2 material by Pablo's group. Mandar's group showed this twisted double bilayer graphene can actually show this nonlinear transport as a probe for topological transitions. And recent studies in HBN graphene MoirÄ also shows this nonlinear transport both in longitudinal and Hall directions. Now, to summarize, these earlier studies mainly talk about this Hall response in twisted double bilayer graphene and TMD. But the recent studies also shows these both components. Now, one thing that was lacking was the extensive study of the longitudinal nonlinear component, which is something that we wanted to look at. And secondly, we wanted to address the quantitative studies that how these different responses, different contributions, intrinsic and extrinsic effect can actually influence this nonlinear transport. And lastly, we wanted to investigate if it is possible to probe to utilize this nonlinear transport to probe this intricacy of the band topology in twisted bilayer graphene. Okay. With this, I introduce you to the system that we will be working on, which is the twisted bilayer graphene. So twisted bilayer graphene inherently holds the inversion symmetry. So we have to break it somehow. One option is to edge align with HBN. Another to put some few layers of TMD material on top of twisted bilayer graphene. We opted this second option, which is basically to put WSE2. Now, this is how the device structure looks like. We have twisted bilayer graphene in close proximity with few layers of WSE2, and this whole ensemble is encapsulated by 2 layers of HBN. And this is how the device structure looks like and the measurement scheme. The first thing to do with this kind of twisted bilayer graphene is to know the twist angle. We basically use this longitudinal resistance and Hall resistance as a function of density. So first you see a peak at charge neutrality point, which corresponds to nu equals to 0, and you see huge peaks at nu equals to plus minus 4, which corresponds to the band gap. From here we calculate the angle to be 1.17 degree. This is a very known picture of twisted bilayer graphene, which is basically a longitudinal resistance as a function of both top gate and back gate. This feature right in the middle is basically corresponds to nu equals to 0. That 2 very high peak of RxX basically shows nu equals to plus minus 4, the band gap, and the correlated features shows these small peaks in RxX by plus minus 2. This is a well studied and known phenomena. What was interesting that when we look at this XY and XX 2 omega components, we see a very similar phase space. So you see these high values of this nonlinear transport at charge neutrality point nu equals to plus minus 4, and even at these different integer fillings. So first thing what we wanted to do is to know how these different contributions are actually affecting. So to do that, the best way and known way is to get a relation between this normalized Vxy 2 omega, which is normalized by this linear component of voltage square, as a function of the first order conductivity, which is sigma. So, and these different terms, these different coefficients, A1 corresponds to skew scattering, A2 corresponds to skew scattering and side jump, and A3 not only includes the scattering mechanism, but also the intrinsic Berry curvature dipole. Now, experimentally, how to get that? Basically, we measured this Vxy 2 omega and sigma simultaneously as a function of a single parameter. We chose temperature for this. This is how the temperature dependence look like for this normalized Vxy2 omega and sigma. For each of these different temperatures, we basically got these two different points of these two different parameters and we plotted them. And this shows a quadratic behavior which matches quite well with the theory. Now, this is something that already reported and was shown earlier. What we could do is basically our theoretical collaborators, Professor Amit Agarwal and Harsh, they calculated the exact similar relation for the longitudinal component, which was not done earlier. And all these different A1 prime, A2 prime, A3 prime, they are quantitatively and qualitatively different, but the overall relation is very similar. And experimentally, when we looked at this xx2 omega normalized version of xx2 omega as a function of sigma, we basically saw an exact match with the theory. Now, the problem was that all these different coefficients of A1, A2, A3, they had these contributions in themselves coupled to each other. So experimentally or theoretically, we could not really isolate each of them. Instead, what we did was to basically use this nonlinear transport as a probe to tune the Fermi surface malleability in twisted bilayer graphene. Now, before going into that, I will briefly introduce the malleable bands in twisted bilayer graphene that we want to probe. So in case of these graphene systems, what can happen, there can be these high diverging values of density of states in the bands. When the Fermi energy reaches this these high values of density of states, also known as van of singularity, this Fermi surface, Fermi contours across this k and k prime, they merges, which alters the Fermi surface topology, which basically results in this sign change of the charge carrier type. So initially you have an electron-like, and it suddenly from that particular point, it becomes hole-like. It's also known as Lifshitz transition. The best way to probe is to look at the Hall density. So the Hall density you see near this 3.5 filling factor, we see a sign change. Now, in addition to that, in case of MoirÄ and twisted samples, the bands become very malleable. So when this Fermi energy reaches this van of singularity or high values of density of states, instead of changing the sign, the band can split, causing a huge reduction in the density of states. So what happens, instead of changing the sign, initially this charge carrier diverges, but it does not go to the basically it does not change the sign. Instead, it reduces and starts to increase again like an electron-like. Again, it's a Hall density measurement which can probe it quite well. So this is in the negative side. So look at the magnitude. Initially, it increases, then decreases, then again increases, and this is known as a reset behavior. Now, all this Lifshitz transition and reset, they are well known and basically probed earlier in twisted bilayer graphene. Now, all this measurement was done at a magnetic field of 1 Tesla. What was interesting, first we will look at this Lifshitz transition. This is how it looks. And if you look at the exact same range in the nonlinear transport data without any magnetic field, we could see these sign changes, and both in the longitudinal and Hall 2 omega components. Secondly, if you look at this reset, which is close to this nu equals to -2, if we look at the nonlinear transport, it shows that exact similar behavior. First it decreases and it starts to increase again. Now this mainly happens because there is a huge reduction of the density of states, so the charge carriers are also less for scattering, which contributes to this less reduced values of this Vxx and Vxy2 omega. So basically we have these two different probes which are basically tuning the same physical states, one with the time reversal symmetry and one without. So it does not depend on the magnetic field that if it's present or not. These physical states in twisted bilayer graphene are very inherent and intrinsic to the system. Just to add, this theory shows that this kind of reset and this sign changes are there as you change the energy, and both in this conductivity, second order conductivity for longitudinal and Hall directions. And with this, I want to conclude the talk. To summarize, the observation of both nonlinear transport in the longitudinal and transverse direction at different integer fillings. We study this Berry curvature dipole and skew scattering effect in the system. And lastly, our work establishes this nonlinear response as a robust magnetic field free probe for the band malleability. I would like to thank my supervisor, Chandni, Saishab, with whom I did this work, our theoretical collaborators, Professor Amit Agarwal and Harsh, and for supplying excellent quality HBN crystal, Taniguchi and Watanabe. I would like to thank the funding agencies, and thank you.
Okay, questions?
Berry curvature dipole does not. So you don't in the V2 omega. You don't see any sign change.
No, V2 omega we see sign change.
Because I saw that sort of there.
So here we see sign change, and actually I will show you the this data. So here V2 omega we see sign change at charge point and multiple sign changes over n equals to plus.
And did you do any IV characteristics? Is this V2 omega purely from?
We did. I have not included, but it comes as a square. Because we have these different components, so you know these equations which has coupled all these terms, and we have realized that because of these high values of Vxx to omega, so we have scattering in the system. So it's very difficult to actually isolate the Berry curvature dipole term from this. Yeah.
Okay, thanks.
So all these measurements were done at 1.52 Kelvin around, 2 Kelvin around. Other than that.
Do you expect to see any signatures from correlated states?
So so you can see these values of Vxx to omega and Vxy to omega, which has like some microvolts. Actually, these can come from the correlations. That something that we don't know. We don't claim for that, but it can be coming from these correlations.
Thank you for the very nice talk. If I remember well, you can estimate if you're in a regime for intrinsic or extrinsic from the conductivity and its temperature dependence, at least
Correct.
in other systems. So how does that pan out here?
So you see this term. Now, in a system where the scattering is very less, so basically where you can see this almost 0 Vxx to omega, there you will be able to know this kind of like basically this A3 terms has this Berry curvature dipole. So you can say the scattering is less, and using this A3 term you can calculate that. But problem is that our system has both Vxx and Vxy to omega. So we can't really negate the scattering fully. So in general, this A3 term also has this scattering and Berry curvature dipole. So we could not really isolate.
Okay, thank you.
Okay, any other questions? If not, let's thank Suvronil again. So this concludes the session.